Good morning or good afternoon or good evening, depends on when you're watching this video. What we're going to be looking at today, this is for the spectroscopy lab, also known as the flame test lab. And so what this video's purpose is to show you how to work some of the equations that we've been looking at in lecture and to help you out with the flame test lab that we have. The questions that we're going to be looking at today are the pre-lab questions for the flame test lab. So you might want to have that out and look through it, and it'll, like I said, it'll give you practice on how to use the equations that we have. And so everything that we're talking about in this lab goes back to what Bohr was saying about our electrons in these different orbits. And remember, as they go from one orbit to another, they're either absorbing or emitting energy. And so for the for hydrogen, which is what he was looking at, it only had one electron. And he was saying that this color right here was because the electron went from the first energy level to the second energy level. And then we had a different color when we went to the third, and then so on and so forth. And so what we're going to be looking at are the different energy levels, how much energy is in each of those energy levels, and the wavelength, because we can figure that out, because remember Planck said that there's a relationship between those. Now the first thing I want to look at, and I know I keep listing these, and so you're probably like, okay, I should know these by now. And it's really important that we do know. And let's look at all the equations that we have that pertain to energy. And I know we looked at some in the thermochemistry section, but I'm talking about the equations for energy that pertain to the electrons and everything that goes with that. So the first one that comes to mind, and it's probably because it's based off of this lab that we're looking at, is we said that energy is equal to negative 2.18 times 10 to the negative 18 joules over n squared. Now remember, this n is equal to the energy level. Or it could also be called a principal shell, and there's a bunch of different names for it, but energy level or principal shell are going to be the ones that we look at most commonly. Now when we look at energy, yeah, we want to know how much energy the electron has, but what we really are looking at is that change of energy. And remember, the delta sign here means change of. And so anytime we have the change of anything, it's going to be the final minus the initial. And so we can look at this equation and we can actually combine these two. And we can also say that the change of energy is equal to this negative 2.18 times 10 to the negative 18 joules over our n squared. And this would be our final energy level. And then minus negative 2.18 times 10 to the negative 18 joules over n squared. And this would be our initial. Now, I did show you guys before in lecture where we can clean this up a little bit. Just kind of depends on which way you feel most comfortable with. Is we can also say that the change of energy is equal to negative 2.18 times 10 to the negative 18 joules times the inverse of n squared minus n squared of our initial. Whichever way you feel more comfortable with is really what I would recommend you to use. Now with that, we also looked at the beginning of the chapter that the change of energy, and this is something that Planck was looking at, is equal to h times the frequency. And frequency is measured in per second. H is Planck's constant, which is that 6.626 times 10 to the negative 34 joules seconds. Okay, so that's one way that we can look at it. And then we also said that the change of energy can also be equal to h times c, and in this case c is the speed of light over the wavelength, and wavelength here has to be measured in meters. Okay, so that's really important that you have that value in meters. And so h is still that 6.626, and c here is equal to 3.00 times 10 to the 8 meters per second. This meters per second is the reason why wavelength has to be in meters. All right, and so taking a little bit further, just another equation that we talked about was the speed of light is equal to frequency times wavelength. We might come back to that one here in just a second. So here's the equations that go along with the chapter that we've been looking at. And I know I keep saying this, and I know I sound like a broken record. It helps to have these listed, and we'll come back to these as we start looking at the problems. Okay, so the problems, like I said, that we're going to start working on are in the pre-lab for this for the lab that we're looking at. you will be conducting the virtual lab. It shows you the same things that they got to see in the real lab. You'll be doing the same thing. It's just you'll see a picture of what they got to see in real life. So the first question asks, calculate the energy of an electron in the fifth principal shell. So principal shell means that it is N. And so we're saying that N is equal to 5. So for listing out our given information, that's pretty much all that we've been given. All right, so if we go back and we look at our list of equations, because we're asked to find our unknown here is calculate the energy. So we're looking for energy here. Okay, so if we go back, maybe. Okay, so if we go back to this, what we have going on here, okay, I'm going to look through my list of equations. So I have a bunch that have energy change into them, but I only have one that has one energy level. So we're going to look at this equation right here, and that's the equation that we're going to use because we're only given energy level or principal shell, however you want to look at that. Okay, and so our equation is going to be energy is equal to negative 2.18 times 10 to the negative 18 joules over N squared, which means we're going to substitute here. And so energy is equal to negative 2.18 times 10 to the negative 18 joules over, that needs to be, oops, 5 squared. Okay, so when I plug this into my calculator for the solving portion of this, the energy that we are given is equal to negative 8.72 times 10 to the negative 20 joules. Okay, now when we look at this, don't forget the negative, okay, because that's part of the equation. It's always going to be a negative value when you're calculating for just that energy level that's there. We go with 3 significant figures because this 5 right here is a counted number. It's a whole number. It's unlimited, so it doesn't limit us. And so we're limited by the given or the constant in this equation. So that's where we have the 3 significant figures. All right, so that's how much energy every electron has that's in that 5th energy level. And there are 50 electrons that can fit in that 5th energy level. So there's 50 electrons that have this much energy. So I know it doesn't seem like very much because it's minus 20 joules or negative 20. It's raised to the negative 20th power. It is a very small amount, but remember joules are in a lot of energy, and we're talking about something that's really, really small. But that's how much energy each electron has. Okay, so the next question, question number 2, calculate the energy of an electron for the 3rd principal energy shell. So once again, our given is we have N is equal to 3. All right, so if we go back and we look at the equations that we have, the only equation, once again, is that first one that's listed. And so we're going to use that equation again. So our unknown is we're trying to find the energy. Okay, our equation that we're going to use is negative 2.18 times 10 to the negative 18 joules over N squared. We're going to substitute. And that would be 3 squared. And then go ahead and try to solve it. Now, the cool thing about these videos is you can pause me, put it into your calculator, see if you get the same thing that we get. Now's a really good time to practice so you can make your mistakes here and figure out what mistakes you've made. Okay, so our energy here, oops, I left. Energy is equal to, so the energy that I got was negative 2.42 times 10 to the negative 19 joules of energy. Hopefully you got the same thing. Once again, 3 significant figures because we have 3 significant figures here. All right, so we've calculated the amount of energy. So all of the electrons in that 3rd energy level are going to have this much energy to them, okay? Let's go on to the next question. Now we want to calculate the energy emitted when an electron falls from the 5th energy level to the 3rd. And so we have 1, 2, okay? So we have an electron that's on this 5th energy level right here. And it's going to go down to the third. Now remember, I said when it falls down, it emits energy. It gives it off in the form of light. Now either it's visible light that we can see, or it's one of the electromagnetic spectrum lights that are available. It just depends on how much energy it actually has. And just kind of spoiler alert, that's what we're going to actually try to figure out, is what wavelength does this energy actually give off. And so we want to calculate the energy that's being emitted when we go from the fifth energy level to the third. And so here we have two energy levels. We have a final and we have an initial. So on our givens, the first thing that we need to ask ourselves is, which one is our initial? What is our initial here? Where are we starting at? That's right, the fifth energy level. Okay, and so our final is going to be the third energy level. Now our unknown is we want to find the energy being emitted. So that's going to be our change of energy. So let's go back and let's look at our equations that we have. And we're looking for change of energy. Okay, one we have is final minus initial. Another change of energy is right here where we had the energy levels that are being changed. Now remember, we calculated these values up here on the first two questions. Okay, and then we also have, that's the same thing. We can't use this equation because we don't know frequency, and we can't use this equation because we don't know wavelength. And this is talking about speed and wavelength and frequency, so we can't really use that one either. So I'm going to come back and I'm going to use this equation right here. And the reason why is because we have already calculated these values. Now, if we hadn't already done that, then I would go and use this equation. Now, if you're not for sure, then use this equation and come back and check. You should get the exact same answer that we're going to get on this. So let's go up. Okay, and we said that another given, this is coming from the previous, all these questions are building on each other if you haven't figured that out. Okay, so we said our energy, our final is our third. So the energy from our third principal shell, we said was negative 2.42 times 10 to the negative 19 joules. And then we said the energy from our fifth is going to be that negative 8.7, it's going to be negative 8.72 times 10 to the negative 20 joules. Okay, and so we said that our third is our final and this is our initial. So the equation that we're going to use is this change of energy is equal to energy final minus energy initial. And we said that our final was 3, so here's our final, and our initial is 5. And so we're going to take negative 2.42 times 10 to the negative 19 joules and subtract it from negative 8.72 times 10 to the negative 20 joules. Okay, now be careful with the negatives here and the double negative that's going on. So when we look at this and when I plug this into the equation, I get, so here is the substitute, the solving part of it. I got negative 1.55 times 10 to the negative 19 joules. Now it's saying it's emitting energy. That means energy is leaving, which means it's an exothermic reaction. So we got a negative value, which means it's exothermic. So based off of that information that we have, we do have that negative sign helps verify that we are in the right ballpark. At least we have that negative value that's there. Okay, so that means that when it is going from the fifth energy level to the third energy level, we're losing this much energy. And it's in the form of some wave and some light. Now, if we go from the third energy level to the fifth energy level, it has to absorb energy. How much energy does it have to absorb? That's right. It has to absorb the same amount of energy to go from 3 to 5 as it loses when it goes from 5 to 3. Just like all the other reactions, when you reverse it, the only thing you change is the sign. The amount of energy to get from point A to point B is the same as it from point B to point A. It's just a different. One's either gaining energy and the other one is losing energy. Okay, so the next question asks us about this. What is the wavelength for the photon of the light being emitted? Okay, so we got to look at this and just some of our givens that we have. And really the only given that we have is this change of energy, and it is equal to that negative 1.55 times 10 to the negative 19 joules. Now this negative is pretty important, especially on the first problem that we solved. But when we talk about the wavelength for the light, like we said, it doesn't matter if it's going forward, if it's going backwards, it's going to be the same energy, so the wavelength is going to be the same. And so when we start solving for wavelength, we're actually going to take the absolute value of this number. And so I'm going to put on here is the change of energy is 1.55 times 10 to the negative 19 joules. Okay, our unknown, what we're trying to find here is the wavelength. So let's go back to our nice little list of equations that we have. Okay, so we're trying to find wavelength. So I'm going to go through, scan. Okay, I have two equations right here that have wavelength in them. The first one, I have H, that's a constant. I have C, that's a constant. And here's wavelength right here. Now I also have this change of energy, so this is a good possibility. The other wavelength equation I have is right here. I don't know frequency. I know speed of light, but I don't know frequency. So I can't use this because I'm missing two variables. So the equation that we're going to use is this equation right here. Even though it doesn't say wavelength is equal to something, we can use algebra to solve for the wavelength. And so let's go up here. Okay, and so the equation that we're going to use is change of energy is equal to hc over the wavelength. Now our next step is to substitute. So let's go ahead and let's manipulate this equation. Okay, so to get wavelength by itself, the first thing that we need to do is we've got to do the opposite of what's going on here. And so the opposite of dividing by wavelength, we're going to multiply both sides by wavelength. And so I end up with wavelength times the change of energy is equal to Planck's constant times the speed of light. And then I'm going to divide both sides by my change of energy. And what I end up getting is wavelength is equal to hc over the change of energy. Okay, and in this step we also start substituting our numbers in. So we have wavelength is equal to the 6.626 times 10 to the negative 34. 3.00 times 10 to the 8 meters per second. I'm going to squeeze in joules seconds right there. Sorry, I forgot to put my units. And then my energy, we're going to go with the 1.55 times 10 to the negative 19 joules. My joules cancel out, my seconds cancel out, and I'm left with meters. What do we measure wavelength in? That's right. We measure it in meters. Okay, so wavelength is going to be equal to, when you plug it all in, okay, I got a positive 1.28 times 10 to the negative 6 meters. Okay, so that's how many meters the wavelength is. Now the reason why we took the negative off on this is because we can't have a negative wavelength. And so if you didn't take it off, you're like, I don't know if I should take it off or not, and you have that negative right here, what you would actually end up with would be a negative number. And so if you think about it, we can't have a negative wavelength, and so you could just remove that if that helps you out on there. But this should be a positive number, and that's why we took the absolute value of that. And so the wavelength is the same if we're going from 3 to 5 as we're going to 5 to 3, and so that it doesn't matter what direction that you're going from there. It's still the same wavelength because it's the same amount of energy that's involved. And what this equation is saying is that the change of energy and the wavelength are related to each other. Okay, so let's look at our next question. It wants to know what is the frequency for this reaction that's taking place. So once again, it has no numbers that are listed, but we do know a couple things. First thing that we just solved for the wavelength, and we said the wavelength was equal to 1.28 times 10 to the negative 6 meters. So that's a value that we have. We also know that our change of energy for this reaction is equal to 1.55 times 10 to the negative 19 joules. Okay, so there's two givens, and we still know Planck's constant, and we also know the speed of light. So that could be something that could help us out. So let's go through and let's look at our list of equations and see if any of those would help us solve for it. This isn't going to help because we don't have energy level, and we've already used that equation. We're not given a final initial, and it's asking about frequency. So really what we need to do is look through here. We got one equation right here that has frequency, and then we have another equation right here that has frequency. And so the question we got to ask ourselves is, they're both three variables, do we have two out of the three numbers? And right here we do. We know the change of energy. We know Planck's constant, so we could solve for frequency. Here we know the speed of light. We know the wavelength, and so we could solve for the frequency. Now we could use both of these equations. Both of them would be correct, and we would solve for frequency the same way. I'm actually going to use this equation right here for no other reason other than if we use wavelength, we've manipulated that number twice. Okay, and so it's two equations or two steps for us to get this value. On our change of energy, we've only manipulated the number once. We've only solved for one number. So I'm going to use this equation here. You can use this equation and you should still get the same answer that we got before. Okay, so going back, my unknown is going to be our frequency. Okay, and so the equation, like I said, I'm going to use is the change of energy is equal to Planck's constant times frequency. Now frequency is not by itself, so I'm going to solve to get it by itself. Okay, divide both sides by Planck's constant, and I get frequency is equal to the change of energy over Planck's constant. Okay, still substituting. I'm going to take frequency is equal to that 1.55 times 10 to the negative 19 joules. And I'm going to divide it by the 6.626 times 10 to the negative 34 joules seconds. My joules are going to cancel out, and I'm left with per second. So that's a good sign. My units are at least lining up. And when I do that, I end up getting 2.34 times 10 to the positive 14 per second. So the frequency of this photon is this value right here. Now, once again, I use the absolute value of my change in energy. And so when I did that, frequency is going to have a positive value. So if you use the change of energy that we calculated and you had a negative there, you're going to need to take the absolute value because frequency is always going to be a positive number. Now, if you did go through and you said, okay, I wanted to use this equation because this just makes sense to me, you would do the same thing. Is you would set it up, you would solve for frequency, so we would divide both sides by our wavelength, and so we end up saying that frequency is equal to the speed of light over the wavelength, which is equal to 3.00 times 10 to the 8 meters per second. And we said our wavelength was, hold on, let me find it real quick, was 1.28 times 10 to the negative 6 meters. Meters cancel out. Now when you plug these numbers in, you get 2.34 times 10 to the 14 per seconds. Okay, and so you still get the same answer. Either equation, like I said, will work. Okay, so then the last question wants to know what type of light is this? Is it a microwave, infrared, or visible light? To be able to do this, you have to look at the electromagnetic spectrum. And you can get this from your textbook, you can Google it, you can get it from your notes. It's a pretty easy thing to get a hold of. Okay, now we can either use, because on this spectrum it's arranged by wavelength or by frequency. Now on here, we're going to look at frequency, and the reason why is because my wavelength on this spectrum is measured in nanometers. When we calculated wavelength, we measured it in meters. So I could make that conversion, but I don't want to. So we're going to look at it. And we said our frequency was 2.34 times 10 to the 14th. And so I'm going to come along my frequency, and I'm going to find 10 to the 14th. Okay, so what you're really looking at is your scientific notation, that exponent that you wrote on there. And so times 10 to the 14th is going to be in this range right here. So what kind of light would that be? That's right. It's an infrared light. Now, so that would be heat that would be given off. And if you had infrared goggles, you would actually be able to see it. We can't see it with the naked eye. You can kind of feel it a little bit. Sometimes depends on what range it actually is. And so this would be an infrared light that is given off. So remember, whatever's given off when those electrons are changing are going to be somewhere on this spectrum. Okay, what we can see is what's right here. And so that is the pre-lab portion of this lab. Now what you guys are going to do is you're going to log on to the website that it asks you guys to log into, and you're going to make a data table all of your own, and it's going to, and on your instructions it has a list of the information that needs to go on there. The first thing that you're going to list is going to be the formula for the solution. All the solutions are chlorides. Okay, so in other words, it has something blank chlorides there. And so when you look at it, the first one, I don't know which one the first one is on there, but you could have like sodium chloride. And so on your first column, you would NaCl. Okay, and then you would name that sodium chloride. Now the next column that you guys are going to make, so here would be your first column, and make sure you label these, not just 1 and 2. Your second column is going to be the metal ion that is making up this solution. Now remember, you got to look at these. These are all going to be ionic compounds, so one of these is metal and one of them is a non-metal. So the second one, you're going to list it out. So it's going to be a symbol with a charge to it. Okay, is it Na plus? What is that charge? Is it Cl minus? You're going to list the metal ion there. Okay, then in the next column, you're going to list the color of the flame. When you see that, you'll look at the picture, you'll list the color of the flame. Now on your handout, there is a table that has wavelength, and I may have this backwards, wavelength and then color. And so, and it's broken down, and it has the different colors, orange, okay, and then it has some wavelength there. If you see an orange wave, then you're going to go with the wavelength that represents that color. And so that's how you're going to pick that out, and you're going to list the wavelength. Now this wavelength is measured in nanometers. Okay, and so then in your next column, it tells you to calculate your wavelength into meters. And so you'll need to use the conversion that I've been giving you guys and going over in class on how many meters are in a nanometer. If you remember, it's 1 times 10 to the negative 9 meters are in a nanometer. So you're going to make that conversion. And the reason why we make that conversion is none of our equations allow us to use wavelength in meters. Okay, but the table that you're given gives it to you guys in nanometers. And then what you're going to do is it asks you to calculate your change of energy. Okay, now change of energy, if you guys don't mind, I'm going to go back again to our list of equations. You're going to pick one of these equations that has change of energies. We don't know the energy levels. It's kind of something that we're looking at, trying to find out. So these are going to be taken off. Okay, the other two change of energies is going to be H times frequency. Did we calculate frequency? Nope. And then the other one that you have is this with wavelength. What else is on your table? Wavelength. And so you're going to use this equation to figure out what that change of energy is. And you're going to record it into your data table, into the column that is delta E. Okay, be sure that you show your calculations. Make sure you show all your calculations when you convert wavelength from nanometers to meters. Make sure you show all the calculations when you're calculating your change of energy for each of these. Okay, after you do this part of the lab, there's also a list of unknowns. Okay, and those unknowns are things that you've already seen before, and I want you to list unknown number 1, number 2, however many unknowns are listed, and then you're going to record the color. Okay, and then identify the ion. Okay, so you're going to figure out what is that metal ion that's making it, and it's going to be something that you saw previously. And so if you see an orange one before and this one's orange, then you go back and see which one you saw orange with, and that's going to be the ion. If you have multiple ones, look and compare. There's a slight difference between those oranges, and so then you can go back in and compare those. Okay, and so that's going to be the data that you're going to collect. Then there are some post-lab questions. There's some more problems that you guys are going to work. They are similar but a little bit different than what we've been looking at. I can guarantee that you're going to use some of these equations right here. So list out your givens, get in the practice of going through and figuring out what equation are you going to use with those, okay? And that will help you guys out when you start solving those problems. Now, your next lab is, this is the Lewis Structure Lab is going to be the next lab that we have. It starts on page 129 in the lab manual. And I have some good news for you. There's no pre-lab. So 2 weeks in a row, you guys don't have a pre-lab. Enjoy it while it lasts. And you'll just bring this to class and we will go through it. Now, I do want you guys to turn in your thermo lab. And that's that Therm 346 lab needs to be turned in. And how you guys are going to turn it in, and you'll staple it, okay, is I want your post lab, and I don't know the page number, so list your post lab. And then I want data sheet 1 and 2, and this is in numerical order. But then after data sheet 1 and 2, I want you to list the calorimeter constant table, okay? And this is the one that you printed out, the one that I sent you. It was a PDF file. I want the table listed, okay? And then I want the graphs. And there's 2 of those, and that's from the calorimeter constant. And put them in order, trial 1, trial 2. Then I want you to put data sheet 3 and 4, okay? And then from last week's lab, your neutralization table with both those. Make sure you label which one was your acid and which one was your base, and graphs, and you'll have 2 of those, and you'll put those, put those in there. And then after that, you'll have your pre-lab graph, okay, and then you'll have your pre-lab problems. And that's the order I want you guys to turn this in. I know we're not meeting on Thursday, but I would like to have these turned in before Friday if all possible. And because we're not meeting and some of you guys don't come up to campus on Friday, I am going to offer 10 bonus points. Okay, I know before I've offered more, but this is something you guys should have already had done, should have already been working on it, because we just found out that we weren't going to be meeting. And so if you can get it turned into me by then, I will give you guys extra credit for that. This is all for the labs, so go to that website, look at the different flame colors of what's going on with those reactions that are happening or those compounds, and complete this lab. This lab, the flame test lab, will be due the next lab that we meet. So make sure that you have all of that completed, the data table and everything made up. If you have any questions, don't hesitate to contact me, and I will talk to you guys later. Have a good day.